Let me read it back. Yes, I'll keep it to size. Right, now for something completely different. We're into econometrics. And of course, all macro models are based on incomplete, incorrect, and changeable theories. The time series are aggregate, inaccurate, and rarely match our theoretical concepts. Empirical macro models always turn out to be non-constant after the fact. We know they're misspecified in numerous ways. Economic policy often has unexpected effects different between prior analyses. And economic forecasts regularly go badly awry. So how are you going to choose between alternative approaches, all of which are problems? At the moment, I would have said the main justification, and it's come out a lot in the conference, is conformity with conventionally accepted economic theory. Internal credibility as against verisimilitude. And this is partly justified by people who take this line by inadequate, short-dependent, heterogeneous time series, often subject to extensive revision. The data are unreliable, better to trust the theory. But theories have evolved greatly. We've seen that even in this conference. And most previous analyses have been abandoned. So it's almost self-contradictory to justify an empirical model by an invalid theory that you know will soon be altered. Why is incorrect and mutable theory more reliable than data evidence? Now, worries concern the prevalence of non-stationarity, endogeneity, potential lack of identification, linearity, a belief that data mining can produce almost any desired result, but so can theory mining. Theory choice by matching non-existent stylized facts that are neither constant nor facts can produce the stylized. Another part of the belief is a mistaken conflation of economic theory models of human behavior with the actual underlying data generation process in the economy. There's an enormous gap between abstract theory, which is often stationary and equilibrium, and non-stationary evidence, finessed by asserting that the model is the mechanism. The final part is a false belief that database model selections are subterfuge of scoundrels, rather than actually the key to understanding the complexities of macro. Now, reality includes unanticipated shifts. People build models, they assume distributions, they make inferences around the distributions. The distributions might be fat-tailed, or black swans may appear, but if they appear, they ought to appear equally in either tail. What's actually happening, in my view, while we get flocks of black swans all happening and they're highly correlated, is the distribution has shifted. And it shifts regularly. Mike Clements and I have done lots of studies of historical data from time immemorial in Britain 1860 onwards, and you do get unanticipated location shifts intermittently occurring. Now, I can't discuss all the issues about credibility and verisimilitude. I think both matter. And model selection, while retaining but not imposing the theory. You have a theory, I'm going to show you how you can retain it. The distribution of your parameter estimates are identical to what you would have got if your theory were perfectly correct. But you can embed it in an enormous number, many more variables and observations, and do model selection, and yet the distribution of your theory parameters is identical. But you're protected against every seminar question that could ever occur, because you've looked at everything before you did it. We need to tackle multiple location shifts, and we need to test the validity of policy models before we use them. So we're going to nest theory-driven within data-driven approaches, retain all the theory insights, unaffected by selection, but we're going to select over everything else. Variables that might have mattered but weren't in your theory, other people propose, long lags, functional forms, multiple breaks, etc. And all of this can be done without in any way, shape or form affecting the distributions of your parameter estimates. And it can be for more candidate variables n than the sample size t, and it's essentially costless if your theory is correct. Now, I attribute a zero probability to that. So what's going to happen is you're going to learn a great deal when you do this about what's wrong with your theory, what directions hasn't it catered for. And this will be done showing that model selection has precisely the opposite problems to current beliefs. So what happens currently is discoveries in economics have mainly come from theory historically, but we know theories are incomplete, incorrect, and mutable. We know that they're inappropriate to make ceteris paribus assumptions because we do live in a non-stationary, evolving world where unanticipated events happen. So you can't take ceteris paribus to data. It's meaningless. take any economic analysis, there's hundreds of assumptions about what's going on, the form of utility or loss functions of agents, which constraints they face, what information they possess. And you hear people say, I'll assume relative risk aversion or absolute risk aversion. I'm going to take this constant attic sudden, blah, blah, blah. We're aggregating across heterogeneous individuals whose endowments have shifted dramatically over time, often quite abruptly. The economic analysis also changes the world, right? Adam Smith's invisible hand led to the abolition of the Corn Laws further down the road. We know that option pricing affects markets, options and contracts. Think of Paul Klemperer's work in the 3G, or 2G, whatever it was at the time. Moral hazard comes in, asymmetric influence, all of these things really matter. But imagine imposing 1900s economic theory in empirical research today. People would think you were daft, but that's what's going wrong with the profession. People are imposing theory which will be abandoned. And when it's abandoned, the data, supposedly, the learning, the information we had, gets abandoned with it. Because its only justification was that theory. It had no stand-alone empirical justification. So we get fads and fashion, schools and cycles and all the rest in economics. And the trouble with econometrics up to very, very recent times is it was totally inadequate to the task it was trying to address. I have lots of sympathy for people branching out into other areas and trying other things, because unless you dealt with everything jointly, simultaneously in modelling, all the substantive effects, because the world is changing, you will get a model that breaks down quite quickly, right? So that, why not then trust your theory? At least you understand it. So starting from T observations and N variables, let's call them W, we want to find the coefficients of quite complicated nonlinear lagged functions of all those variables jointly and simultaneously with all the breaks that are going on, and at the same time embed the initial economic theory inside, because it might well be right, in which case we can do much better. And it leads to an approach which has created a bit of a stir, at least in European scientific discovery, the philosophy of scientific discovery, because globally learning has to be simple to general. Experiments are stuck in that domain. But in observational disciplines it can suddenly become general to simple, and you can learn a vast amount in one jump. So, how well can we approximate data generation processes? Well, three extensions are very simply done automatically: longer lags, nonlinear functions, and impulse indicator saturation. I'm going to skip, you all know how to set up longer lags. Everyone knows how to take principal component transformations. And the crucial thing in economics is variables are immensely highly intercorrelated. If you take a principal component transformation, you get linear combinations of all the variables, and then individual components, say we call them U are the transformations of W. UIT squared is a squared and cross products involving every possible original variable, and the cube likewise, and exponential functions. There's only 3n of them, not 6n into n plus 1, etc., type. So you get very low dimensional coverage of enormous numbers of possible nonlinearities, and so you can then put in lots of lags of them and the variables. And because we're handling more variables and observations, perfect linearity is irrelevant in here. It just doesn't matter. Right? It may surprise you, I put in all the variables and all their principal components and the nonlinear functions of the principal components at long lags together with an indicator variable, an impulse indicator for every observation. They're all going to go in. So, how do we detect multiple breaks? This has taken a long time to develop. There's a long history of people not understanding quite what they were doing in econometrics. But the Chow test is an impulse indicator saturation test on an assumed period. Recursive estimation is an impulse indicator estimator, because you put in indicators for all the data you haven't used and then you recursively update. What we're going to do is create an indicator for every observation. Then we're going to put them in very big blocks. And we can do this while selecting over lags, variables, and nonlinear functions. And we have a now almost complete theory of how this works and why it's nearly costless, which is quite extraordinary, because we're going to put in t indicators for t data points. Now, it's been extended to stationary, non-stationary unit root autoregressions. Jürgen Durnick and I are working on it for systems. It seems to be very similar. And we've got it for step breaks as well as impulse indicators, but I'm only going to address indicators today. What the Johansen-Nielsen paper shows is After putting in an impulse indicator for every observation and selecting in big blocks across them, under the null that you didn't need any indicators of no breaks, so it's a kind of robust estimation, the rate of convergence is still root t, it still converges to a normal, it's still centered in 0, it's still got the usual sigma squared, sigma to the minus 1 variance covariance matrix, but it's an efficiency factor. You do lose some efficiency. So say I've got 100 observations, I put in an indicator for every observation, I set in big blocks at the 1%, then I will keep one indicator by chance. That reduces the sample to 99 observations rather than 100, because an indicator just removes an observation, and therefore it's 99% efficient to have tested for a break in every possible observation and combination of observations. 99% efficient. Costs you nothing to try the 100 indicator. So let me show you this actually working. If I had my own computer, I'd do it live, but I can just show you the things. The analysis depends on split half, but we actually do many, many different searches because the extra searches cost you nothing. Put in half the dummies. Check which dummy is retained. Here, the null is true, one dummy is retained. Drop that half, put in the second half, check again, none are retained. Combine the two, there's only one here, and it's retained. Under the alternative, it behaves quite differently. So here I've got the same data, but I've put in an arbitrary break of 10 standard deviations. When you put in the first half, you estimate the mean from the second half, and clearly that mean is very, very discrepant, and you get huge numbers of outliers apparently appear. You drop them, you do the second half, that gets another number. Now it says, aha, relative to this mean, this lot is discrepant, so it keeps those. Combine them, and it just keeps the second set. Right? And so you've picked up the break. It will pick up to 20 breaks in 100 data points. I mean, you just can't hope that this is stopped. Yeah. Okay, so now we have our general model. We've got long lags, we've got all the variables, all the principal components, all the nonlinear functions, all the dummies. We can now go to select. But it's not atheoretic. I keep getting told, oh, you're ignoring economics. Are we devil ignoring economics? We're trying to save economics from itself. Keeping it in a context in which it can be empirically relevant and yet keep its insights. So we're going to embed the economics inside the general model. I'm only going to illustrate it for the most trivial setting, which is a regression. So imagine your theory is that y depends on beta z, z is exogenous, beta is constant, the conditioning is valid, the errors are in, not sigma squared. And we all know that beta hat's normally distributed around beta with usual variance covariance matrix. Then after the seminar, and you've been bombarded with things, people have said, oh, you ought to do this, this, and this. So let's call them W. So now we add all the W's in, so the general model becomes 6. It's a much bigger model. It might be hundreds of these things, but here I'm focusing in the case where there's fewer than the number of observations. You orthogonalize Z with respect to W, which gives us the U, and you replace gamma W by gamma U. Now, because the coefficient of gamma is 0, you don't affect the Z, but now you've got an orthogonal model, and everyone knows if you run an orthogonal model, it doesn't matter whether these are in or out. The distribution is identical, and it's very trivial to prove that the distribution in the extended model of your beta is exactly what you would have got in the earlier model, and there's a bunch of other stuff in here. So the only cost of selection are you might retain some of the U's, and we do that by controlling by very tight significance levels, usually 1 over n plus t at the significance level, and you can then determine the distribution under the null of how many U's you might maintain. Check that by Kolmogorov-Smirnov type thing, and then there's an impact of the estimated distribution of the residual variance, and we have bias correction formula, so that can come out unbiased. If the theory is wrong, then of course you'll be underspecified because you haven't got enough lags, but you've got the right set of variables and you haven't got the right functional forms, or alternatively you've actually left out relevant variables. So this is a win-win situation. Your theory is kept valid and complete with exactly the same distribution as you would have had if you'd imposed it in data, but if it's not correct, you get empirical model discovery, vastly more information coming out at almost no cost, whatever. Now this extends to more candidate variables and observations. The way we prove the split half turns out to work if you imagine mutually orthogonal candidate regressors. You can do the same analysis. But then it turns out that you can actually extend this to non-orthogonal variables and more of them than the number of observations. And one of the problems is these breaks occur. Everyone's talked about breaks at various stages during their talks, and these breaks are very important because unless all substantive variables are included and no internal shifts occur, breaks will lead the model to be non-constant. And policy is almost invariably a location shift. It changes the level of things. Consequently, if you've got the wrong model, when you do the policy, you will induce a location shift, which will cause your model to shift. And it will fail exactly when you do the policy. Doesn't matter what class of model, that will happen. There's a bunch of algebra. Oh, I'm way ahead of myself there. Yeah. Bunch of algebra that I'm not going to discuss much. But you can use the same tools and techniques to test for that before you actually do the policy. So that if your model is claimed to be invariant, we've got the y's, we've got the z's in the simple regression context, I model the z's. I apply my impulse indicator saturation to z's to find out when did they shift unanticipatedly relative to their local data generation process. I then take those indicators and put them into the conditional model. Under the null that z correctly represents the information, the beta will not be affected and the added indicators will be insignificant. But under the alternative that the change in the z will cause a shift in the model, when you put the indicators in, you'll reject the null that they're irrelevant. And Carlos Santos and I have several papers showing that you can do these kinds of tests, and that under the null we've got exactly the right distribution. If the z's are super exogenous, you can change them. When you change them, beta stays the same, and y equals beta z after the change. Under the alternative, they've got quite some power to pick up when location shifts occur in Markman models. Now, the case I'm going to use, as apologies to Mark, is the hybrid New Keynesian-Phillips curve to demonstrate that most of what happens there is an artifact of not having modeled the breaks. So we have this theory in which the future inflation of today information impacts on today's inflation rate, and maybe the past does, and then there's some forcing variable. And it's dependent on equation 12, which Neil Erickson queried yesterday, which is that the expectation of tomorrow's inflation, given what we know today, is tomorrow's inflation plus an error. And it's easily proved that the expectation of that error conditional in today's information is 0, and this appears to suggest that this is a good proxy for that, which it simply is not. And that's because these expectations haven't been related to the distribution. This is completely irrelevant because it tells you that you looking forward today think that this thing is going to have a mean of 0. It certainly does not mean it has tomorrow, and therefore this will not be what you think it is. But if you add it, if you replace the expectation, oops, I don't know why that's, by the actual variable under the assumption that 12 tells you something about what the future will be, you'll find that, of course, it picks up all the breaks, because it's happened after the breaks have happened. So what we're going to do instead is we're going to model the delta p not just by the variables that are put into the standard GMM, we're going to do impulse indicator saturation with 14, so we've got delta p and the past in there to find out what indicators matter. And then we can replicate almost exactly what you guys find, right? Isn't that a miracle? I mean, that's so difficult in economics. We got it almost immediately. The sum of the elasticities is 1. The future indicator, the future inflation recording is much bigger than the lag. There's not much significance from the driving factor. But when you do impulse indicator saturation and delta PT with the other instruments in it, we find 11 indicators highly significant. Most of them are oil crisis-based ones. We then find that the gap lag matters enormously to make the model match the evidence, in which case the over-identifying restriction test is insignificant. And 9 of these 11 indicators are significant in the feed-forward NKPC, and the coefficient of delta PT plus 1 goes negative. Never mind 0.65, it actually goes negative and is not significantly different from 0. The coefficient in the wage share now becomes very sizable and highly efficient, and you find almost no inflation persistence in the estimated model. Now, underlying all this, I believe, is a much, much deeper problem. And that deeper problem is a bit of fairly complicated mathematics about intertemporal optimization. If we were to write the distribution today of inflation is f of delta pt as its density function, then what the equation 13 actually said is, today, looking forward to tomorrow, conditional on today's distribution of inflation and knowing what I know about the world, then I expect Vt plus 1 to be 0. But this does not guarantee that tomorrow the expected value of Vt plus 1 is indeed 0, which is what you require for the current expected value to be well approximated by the future value. In fact, the expected future value of delta pt plus 1 given it, which is the integral of it over the future distribution conditional on what we know, would require you to have a crystal ball. You wouldn't need the expectations, you'd know the entire future distribution before it's happened, which would of course mean there were no unanticipated breaks. Now when unanticipated breaks occur, the best an agent can do is to form a sensible expectation, forecasting the future distribution in some way. And if the moments of it alter unexpectedly, there are no good rules for that, except that today's distribution is not a good choice. That's why we get predictive failure in economic forecasting. The model today is using today's distribution, and the mean tomorrow is not the mean from that distribution. It's another mean because of the unanticipated location shift. Now, if we can't do it, agents can't do it, but actually, I'm afraid economic theory can't do it either. If this happens, the law of iterated expectations is mathematically invalid. Right? It's not a theorem anymore. Neither is conditional expectations the usual rule that the expectation of conditional expectation is unconditional expectation. If distributions shift, that is mathematically false. It's like trying to use Euclidean geometry on a globe. Right? It just isn't going to work. And all intertemporal derivations facing unanticipated shifts are either, you can either call them mathematically invalid or empirically irrelevant, whichever you choose, but you cannot plainly work. Right? That is not mathematically correct. So surprisingly, DSGEs are intrinsically non-structural. Their very mathematical basis fails when distributions alter. So they're not just susceptible to the Lucas critique, they're susceptible to every possible shift in the planet because they're derived using a mathematics that fails when that event occurs. Now, I've tried to give a positive slant at the start. If your theory is right, I can embed it, it will cost you nothing, and then say why I haven't used credibility, if you like, because I don't think there is much credibility of modern theory. I don't think it's addressed the fact that the world is non-stationary, not just with unit roots, but with unanticipated location shifts. The recent financial crisis happens to be the biggest we've seen in a long time, but all time series are suffering from them all the time. And that's why we've had so bad forecasts from economic models. But there are ways of forecasting that avoid that. I had them in the original slides, but dropped them because they were too long. But we can automatically create, we have software that will automatically create for you, once you tell me what your x is, all the extra variables, all the longer lags, all the nonlinearities, and all the shift indicators. It'll all be done automatically. All you need to do is tell it x and tell the program, do the generals. Then it will search, but it will search embedding your theory model, retaining it, and it can do it for quite a wide class of theory models, as I've only given a proof for regression, such that if you were right, your specification is retained unaltered, and the distribution of your parameter estimates is unaltered. We select the most parsimonious, congruent, encompassing model, because that gives us an undominated representation. We can get near unbiased parameter estimates, despite all the selection that's gone on, because we know exactly what we're doing during the selection, what the critical values are, and when we'll retain parameters and when we won't retain parameters. So it's easy to come up with unbiased estimates. All the pre-test bias stuff is just irrelevant in this context. And then you can stringently evaluate the results, especially testing the superexogeneity if you want to use your model for policy. Now, location shifts have been the focus of my research now for nearly 40 years. The first forecasting I ever did in the late 60s involved forecasting consumers' expenditure in the UK from 1968, 1 and 2. And I got massive forecast failure because of events that happened after I forecasted. Chancellor of the Exchequer warned the public in the first quarter that they didn't behave themselves. They'd increase purchase tax and sales tax, if you like, in the second quarter. They didn't behave themselves. Expenditure rocketed. He then brought in purchase tax. Expenditure collapsed. My forecast didn't allow for that. Here were two big location shifts in the very first time I tried. This is the last slide, so I'll be done. Now, what's much, much worse for our profession is that if a location shift happens, not only does it cause systematic forecasting by all equilibrium correction models, by regressions, VARs, DSGEs, equilibrium correction mechanisms, GARCH, ARCH, stochastic volatility, they all go systematically wrong, but they all go systematically wrong by going in the opposite direction to the data. If the data go down, because they're trying to correct back to equilibrium, they go up. And you can see this in a huge range of economic forecasts using this class of models. A shift occurs in the world, that we have a crisis. What happens? The models say, oh, it's going to recover immediately. Famously, Lamont in Britain wittered on about the green shoots of spring for 3 years before he was sacked. Because the Treasury's model was doing this to the poor guy. Continually saying, yeah, recovery's coming. It never came, of course, because the model's simply going the opposite direction to data because it's desperately trying to equilibrium correct, and there's a new equilibrium. And however long, if you persist with this model, go back to old equilibrium and never get to the new one. You have to have adaptive methods if you're going to deal with it. The shifts are difficult to predict, but we can mitigate forecast failure by having forecast robust devices. And I believe agents actually use them. They don't use rational expectations, conditional expectations, or models. They use robust devices because they know they can't predict these unanticipated shifts. And the cost of using a robust device as against using the true model is very small to the agent. The loss is very small, and they don't have to build models, and they're immune. They don't forecast the breaks. They suffer as the break happens, but they correct very quickly. Iterated expectations cannot be used to solve models. Conditional expectations are not unbiased in this world. Rational expectations would be systematically biased after shifts unless you revise them, but I can change the parameters of the model to be exactly like GNP falls over the crisis by a large number of different shifts of parameters. And the agent cannot know which of these have happened to update if they have a model. But all of them can be dealt with by a robust device. I can also change every DGP parameter by 100 error standard deviations, and you will see nothing. Absolutely nothing in the data. You will not be able to tell me where it occurred until you have enough data after the break to estimate the model on the post-break data alone without the pre-break data coming in. So agents cannot quickly learn what's changed. They simply can't start. There's a huge identification problem for them of a different time. We can exploit location shifts to test throughput certainty, and when we try to apply these to some of the relationships that have failed to take account of all the location shifts that happened in the 70s with the oil crisis, etc., then you find that the coefficients are radically different, and some references.
Just a few. The green shoots have just showed up, by the way, in the data. As of today.
Right.
Third quarter.
Yep.
Yeah, fair. Growth. Growth in the third quarter.
Okay, well, I'm continuing in the somewhat odd tradition of this conference of choosing commentators who are sympathetic to the talks and not maximizing conflict. So I was trying to think about what I could do about this when I saw David's slides and now his presentation, and realized how, in a typical fashion, there's an enormous amount of detail which is very hard to absorb. So I will try to present a little bit about the forest here rather than the detailed trees that we just heard from David. And I hope that you'll indulge me a little bit, because I am a part-time historian of economics and I am a part-time philosopher. So I try and see this in terms of a bigger picture of the development of the discipline over a fairly long period of time. And the problems of thinking about economics as a science go back a long way, and they probably predate John Stuart Mill, but Mill gives, in the 19th century, a particularly compelling account of what he sees to be the difficulty with doing economics. And essentially the difficulty with doing economics as a science, in Mill's view, is that economies are extremely complex, and it's very hard to apply the kind of experimental methods that you might in physics or chemistry. And he raises a lot of these points in one way or another. I'm kind of modernizing them somewhat, but we're raising the point about there's too many agents, they're all heterogeneous. They have problems of having intentions in a way that the subjects of physics don't have intentions. They have to make decisions, molecules don't make decisions. And we have to worry about institutions and the change of institutions over time. So we have a very complex setup, and Mill's solution to this is to say, look, inductive science is not something that can be applied to economics. Economics is best thought of as a deductive science based principally on our intuitions about our understanding of our own behavior and about rationality. We can articulate that into kind of models in which people make sensible choices in a way that we find intuitively appealing. And how does this relate to data? Well, it's not that it doesn't relate to data. They were perfectly interested, Mill would have been perfectly interested in seeing data, but he doesn't see data as feeding back onto the economic analysis in any particular significant way, but principally as illustrating, well, we know there's 6 tendencies in the world, and if one of them happens to be stronger than the others, we might get this kind of result, and we sort of see that in the data. Stylized facts goes right back in some sense without the name to Mill. So when I see what David is doing here is in part rejecting this Millian vision of a theory ahead of all data. And in doing that, I think he stands in what's pretty much also the great econometric tradition. Because the modern econometrics starts with Habermas's probability approach in econometrics in 1944, and this is a font for a lot of the later development of econometrics. And one of the principal ideas here is that the statistical techniques as they had been developed and were being developed by Habermas and his colleagues at the time can do the work of controlled experiments, and we could do something that Mill perhaps thought was not possible. Now, theory is not unimportant in this. Theory, at least provisionally, is essential to even beginning to set up the empirical problem, to knowing what sort of data to collect or how to have initial thoughts about the data. But the other part of the Habermas program is that those kind of theories, once you have set up the statistical framework adequately, are going to be testable in a well-formulated stochastic model. Probability theory is going to be valid in this case only if you have an adequate and accurately formulated, and I want to emphasize, independent stochastic model. Because we can't have the stochastic model depend entirely on the theory and also then being used as the test of the theory. It has to have a degree of independence so that we have some degree of freedom, or we don't have any kind of test at all. So in this, and this is a point which is often missed by modern readers of Habermas, is that stochastic specifications may require us to base some of our specification on phenomenal information, just how do data behave, and David didn't like the word atheoretic, but the point is something which is not tightly tied to theory, and oftentimes that's going to be an ex post judgment, that we're not going to be able in advance to say what was going on. We have to look somewhat backwards, and we have to have sometimes some ad hoc empirical formulations. But the goal is to get a stochastic account of the data which is rich enough and valid enough statistically that gives us the right kind of statistical properties that we can embed a test into that. Now, another aspect of the Habermas approach, which I think is also, again, not always appreciated by modern commentators, is that it is essentially not an a priori approach. He's often referred to as adopting an a priori theory-first kind of approach, but it's actually a piecemeal strategy of learning from the data, of laddering up from perhaps an initial theoretical, conjecture and working up to something more complicated. And there's a lot of, and you can quote very long passages of Habermas, but I'll just quote the one where he quotes Bertrand Russell, that the actual procedure of science consists of an alternation of observation, hypothesis, experiment, and theory, that there is a going back and forth between the data and the theory in a very important way. Habermas was transmitted to the modern econometrics through the Coles Commission, but over time the Coles Commission methodology itself came to be reinterpreted. It came to have the view that theory proposes something, a hypothesis, econometrics checks it, it's wrong, throws it out. This is the image of the econometrician as the grim executioner of theories. And this approach kind of ignores the need for the independently warranted stochastic model as the condition for testing, as the test bed for theories, that we have to get some kind of formulation in which we can test and check different theories. It ignores the potential for learning from our tests, not for just dismissing the theory, this is wrong, we tested it, it's statistically wrong, and instead we need to find out the ways in which it went wrong as information that help us then reformulate the theory. Now, I could see a calibration as a kind of extreme response along these lines, one in which, in a sense, we're returning to Mill. It all has to come out of our heads. Data's all fine. It's fine. Theory can have implications for data, and we can look and see maybe those implications occur, maybe they don't, maybe they're strong, maybe they're weak. But there's no idea that there's a systematic and disciplined way of working backwards from what you learn from your testing or from observations of the empirical world back to modifying and correcting your theory. So if you listen to Ed Prescott, he says, we start with a well-established theory, but there's no account of how a theory comes to be well-established. And if you're an empiricist, the lack of that kind of account is really quite devastating. And makes you think, well, maybe there's something, Ed Mill thought, deeply wrong with empiricism. So again, I see David as in this tradition which opposes the pushing of theory into this kind of superprime position. So what are the main features here of David's methodology? Well, the first is priority is on the data. We are working an arbitrage between theory and data, and it does have to work both ways. We may have gotten a little bit too far. And it's a focus on facts. I am amazed by the degree to which economists are almost incapable of saying the word fact without the adjective stylized. and they've generally have not, thought through very much exactly what that means, what it would mean to be a stylized fact, and what the range of usefulness of a stylized fact is. The problem with stylized facts is in part it just sets too low a standard. It's not very discriminating between, it's too weak to distinguish among inconsistent theoretical alternatives, so that if we really want to make progress when we have competing ideas about what theories are, we're going to have to get a little bit more serious about how we characterize the data in a way that can be discriminating. So that's one of the important things. Just let's focus on the facts. Second important thing in the methodology is again, this is almost repeating the point about Habermas. That's exactly right, because this is in that same tradition. Is we have to have a well-specified stochastic model where we can feel justified in interpreting statistical tests and probability conclusions from it if we're going to have interpretable statistics. And that model is developed without a lot of strong a priori commitment to any particular theory. And there may be some theoretical commitments, but they're reasonably weak. And this is an important point that David ended on, is it's really hopeless to assume fixed probability distributions. You have to worry about that problem. And I'll come back to that one. I want to finish with that one. The next thing is that, again, it's like Hollow, it's a piecemeal strategy. And this is David's point about globally, everything is specific to general. We simply can't work with a methodology in which you basically have to assume you know almost everything before you can know anything useful. It's like God told us the entire specification of the world, except he just didn't want to tell us the parameter values. That's that's not a very good way to go. We have to have a strategy of learning from the data. Now, it seems to me that the most important idea in this strategy is the encompassing idea, that we can think about two accounts of data, a theoretical account, a stochastic account, or two theoretical accounts, and we can ask the question, does one carry all the information that's in the other, so the other can be dismissed as not informative? So does a theory that's embedded in an adequate empirical model support incremental simplification of the empirical model? That's some evidence in favor of the theory. But it's also one where we can consider two theories and embed them both in the theoretical model and run a horse race. And I think that's going to be important. So David has spent a lot of his career on advocating general to specific. But what I want to is to knock general to specific down a level in terms of its importance intellectually or in the kind of framework, that the more important idea is encompassing. And that the reason why general to specific is a very powerful heuristic is because it is an enforcement of the encompassing property. And it's amazingly effective in the specification search methodologies, which you can show in simulation after simulation, and in fact in very challenging simulations, is remarkably effective in a way that many economists just cannot believe is possible. But I just invite you to do the simulations and you'll see what I mean. And increasingly we're getting analytical results to explain why that's true. So let me just end with the importance of the risk versus uncertainty. We can't usefully assume a world of constant probability distributions. Risk are, who's the Rumsfeld, known unknowns. Uncertainty are the unknown unknowns. And allowing for uncertainty undermines the utility, as David was trying to show at the end, of rational expectations for data, even in the weak form of model consistent expectations. It's fine in the world of the model, but applying it in the world where the probability distributions are subject to uncertainty is going to be difficult. So where are we left with that? Well, we can learn ex post about the changing distributions, and this is the work on the brakes and impulse indicator saturation. So what it means is that uncertainty is not an insuperable barrier to learning what the mechanisms of the economy are, to learning sort of how the pieces fit together and what is really going on underneath the economy. But it's an enormous challenge to forecasting, where we see forecasting as a kind of prevision of a kind of crystal ball. It becomes infeasible to do that kind of forecasting. However, because we can understand the mechanisms, we can also understand and rationalize why there are conventional, or as David was calling them, some kind of algorithms that people can use to adapt to the problem of having uncertainty in the world and not being able to have the crystal ball. We can find tools that help us, and strategies that help us to mitigate our ignorance. We can't get rid of the ignorance entirely, but that means that uncertainty here is a challenge for us, but it's not a threat to all useful economics. I would just very quickly just say, oftentimes when David presents his stuff, he presents it in a framework where the key thing is just variable selection or the sign of variables. And actually, theory often imply very complex consequences beyond that sort of thing. Things like co-integration and long-run steady-state properties or relative covariances. And this all needs to be put into the same kind of general to specific and encompassing framework. And a part of that is because many of the illustrations come out of single equations, and we really have to think in the most useful cases in multiple equations. And I would also say that in like the example he gave of the new Keynesian Phillips curve was really embedding one theory into a stochastic specification and checking that. I think a lot of the emphasis ought to be on horse races between competing theories, because that's the way in which we would could be developing and improving in a kind of orderly way. All those issues are addressable, and in many cases David has addressed them to some extent, but I'm just arguing for more emphasis on them. Thank you.
Thank you. David, do you want to respond quickly to that?
Just two responses. One, yes, we have systems methods. The system does make it vastly more complicated because of the interactions between the variables within the system, and how a theory, in some sense, gets embedded in a system. It's quite a complicated issue, right? Because theories often do end up with single equations, and then you've somehow got to find a way of putting them together. But how they're put together in, say, a DSGE or a Keynesian model or something in between is often quite different. And yes, encompassing is one of the key features that stabilizes model selection. But it's also the fact that the model selection literature is huge and very diverse, and a lot of it has misconceived the problem. I didn't really want to discuss this much, but they often look at all possible models. So if you've got n variables of 2 to the n models, which might be bigger than the number of atoms in the entire universe, we're doing variable selection. We've only ever got the n things to worry about. So we can control probabilities. We can say alpha is smaller than 1 upon n or 1 upon t plus n, and alpha smaller than 2 to the n is meaningless. I mean, you'd have 5,000 zeros before you got the first one in it. The critical values would be so large, everything would be acceptable. So you've got to reconfigure model selection away from the lasso, retina, stepwise, Bayesian methods. All of these have this fundamental problem that we can, at least to some extent, avoid. I don't think I reject Mill. The only bit of Mill I reject is the fact that you don't go back from data to theory, right? And that's what, I mean...
You should reject Mill.
I should reject Mill. I mean, a lot of Mill is very sensible. He is predating a lot of what has happened since. But the step back from data to theory, I think, is quite fundamental and has dominated every science except ours, if ours is a science.
Start with Marcus Miller.
Kevin Hoover said that discussions are often too sympathetic. We need some criticism. So let me supply one. David tells us that the world is non-stationary and the shifts are difficult to predict. But last evening, Paul Tucker said, no, in finance, you know what's going to happen. They're going to go to the edge of the box and they're going to try to break the rules. So it seems to me we really ought to take this very, very seriously. And I think what it may lead to is, well, one of two directions. One is Andy Halliday, let's make the rules simple. Another one is perhaps make the rules much tougher. A move away from light touch regulation to Roman law. In India, it's called Reddy's law. If I don't understand it, you can't do it.
Mm-hmm. Yep.
Isn't this are these the kind of thoughts we should be having, rather than spending our time just looking at statistical procedures? We should be looking at what's going on in finance and how to control the financial crisis.
Yeah, well, I turned down working with Rob Engel in 1982 on Arch on the grounds that finance was for people interested in finance and macro was for people interested in macro. And I think a lot of the financial crisis doesn't come out of finance, it exacerbated it, but it does come out of macro. The situation in the housing markets in various countries, Spain, Ireland, the US, for example, even the UK had quite a big effect there. And it gets exacerbated by the over-leverage and the lack of control and the robber barons at the top of these empires who are stripping off the wealth of the nation for themselves. And a lot of these things are going on, but whether regulation could have stopped that, Peyton Young says it couldn't, right? He has several papers saying that they will do it, right? And maybe that's what you're taking Paul Tucker to say. But to understand how the actual economy functions, what feeds into what, and how quickly, and how large, and how long it lasts, persistence, etc., that I think remains very important. And I did want to say to Kevin, I mean, we've dealt with co-integration in our procedures already. I mean, that's not a terribly big step. The big step It's really difficult to solve is co-integration assumes that you have a well-specified statistical model. You've got to first get the well-specified statistical model before you can look at co-integration, and then it just turns out to be a reduction, like all the other reductions. You just happen to go from I1 space to I0 space. You need somewhat different critical values to do it. That can all be built in.
Yeah, so this is a point about expectations formation. So if agents form expectations by running a regression, sure, you need loads of data to spot the break, and by then it's probably too late. But in practice, we're in an information-rich world. And 5 years ago, almost to the day, I saw a queue of people outside Northern Rock, and I knew something extraordinary was happening.
But you didn't know that in early May when it actually happened. They actually went to the Bank of England, people can confirm, they went to the Bank of England in early May saying, we can't borrow at any rate anywhere on the planet. And the Bank of England, I think, more or less said, oh, you're a stupid bank, you're over-lending, your rates aren't, your checking isn't good enough, etc. So you didn't see it till September.
But there's more to forming expectations in T by N.
In what sense?
But there's lots of information.
Yeah, well, yeah, sure.
Which isn't in these
Well,
statistics.
as I respond, I would have said this to Neil during his discussion, but we actually modelled the flu, the previous H1N1 flu spreading across the US. We had 5,000 variables in there, right? When we do nowcasting, we have at least as many as 5,000. We take account of almost everything that you can see, and the programs can handle that. Now, agents cannot. There's no way you can process that kind of information.
Yeah. Again, just to introduce a criticism, not that I disagree with much of what David said, but no, sometimes we have to think of economics not just as the data, but several problems we have. Think of an economy, say a macroeconomy. I've used this analogy before, it's a common one. Think of the macroeconomy as a drunk banging along off the walls of a corridor. Now, that's what you're studying in some sense. What are the dimensions of the alcohol and how much are they banging about? But sometimes we're also interested in a completely different dimension of macroeconomics. Some idiot may have left a door open somewhere, and when drunk accidentally bangs into the corridor where the door's been left open, it falls out. So sometimes we also need techniques to look at the probability of extremely rare events happening. And I think the sorts of techniques you're doing don't do the very rare events very easily.
The one thing I have never managed to get any agency, including the ESRC, the ERC, anybody to finance is a study of how you forecast breaks. Right? Everybody says, oh, you can't do it, it's a waste of time, you're not getting the money. So we've devoted almost no effort whatever to doing it. We recently had a paper, how you do it. And things like the Indian Ocean tsunami that killed tens of thousands of people was completely predictable, right? Absolutely, totally predictable. Within 5 seconds of it happening. It was known to have happened, except people were not looking. It's rather like subprime loans. They were not looking at the geostationary satellite that recorded the earthquake. And you had 10 hours of warning for Sri Lanka, in fact. And you can trace it all the way through. Now, you can't yet forecast the earthquake, right? There are some things. But at very high frequency data, you can pick it up like in the first 5 seconds and start to tell people, this has happened, start being prepared to deal with it.
But maybe we need to be able to forecast the probability of the earthquake. And as the probability
of the earthquake currently in that region is close to 1 over the next 100 years. But they don't know what the probability distribution is over time. And that eludes volcanologists, it eludes tectonic plate theorists, and it will elude them and people like us, because a lot of it is due to chaotic behavior inside the system, how the stresses actually work their way through. I think that applies in economics. I mean, the subprime loan crisis could have happened in 2004 if it started a bit earlier, but it might not have happened for 2 years later if it hadn't shown up such big losses.
Yeah. And therefore we should look at rising probabilities.
Yeah,
yes.
Discuss that first. Dwight,
I'm curious, I'd like to see if you could just articulate a little better how you're dealing with overfitting. Is it the encompassing and dominance that
No, it's critical volume. There's no chance of overfitting under the null zone. None at all.
But so I just want to
say you've got 1,000 variables, we set critical value at 1 in 1,000. Under the null, you'll keep 1 variable. But that variable will be very close to the significance of that variable will be very close to the critical value, because the probability under the null of it being very far from it is near 0. It's almost always within 1.5 critical values of the critical value, where you almost never see a draw, even in 1,000 random variables. So there's almost no overfitting, no chance at all. It's not a problem. Martin's been
There's
desperate.
somebody over here. Yes, Martin.
Yes, I was wondering whether you could give me at least a brief summary of the practicality of it. If I think of what's happened over the last few years, well, maybe someone who had looked in May 2007 would have seen a run, or if they'd been able to peer into the entrails of the Bank of England, would have seen the evidence that something was wrong with Northern Rock. But we know that there have been problems with individual banks in the past, and they haven't had the apparent consequences. How in practice does your mechanism work as a tool of telling people who are trying to forecast when they should throw away what they've been relying on and conclude that actually the world has changed?
Well, as yet, forecasting the breaks is not feasible. We've tried with various cases to look at them. Even forecasting during a break is extraordinarily difficult, because when a location shift occurs, it changes linearities. That affects the root mean squared errors of forecasts very dramatically, maybe 100-fold increase in them from the change in linearity due to the smallest eigenvalue in the system. It's really very dramatic effect, and it's very difficult to get around it. But 2 or 3 periods later, that same change in linearity has given you enormous amounts of information, and suddenly you get very precise estimates of what's happening. Now it takes 2 or 3 periods. Now if these periods were hours, or days, or weeks rather than months or quarters, we could be onto these things very, very much faster. Because if a break happens at a point in time, that's when you get the big increase in root mean squared error. And in high frequency data, yes, noisier, but I'm very, very keen when the data section comes up that we look for much higher frequency data, but we're out of time. We're going to miss our lunch.
Not quite. Martin, you wanted to follow that?
Well, I did want to have a follow-on. No, could I press you on that and think in practice, how long after, say, the development of the contraction do you think people should have concluded that there had been a semi-permanent loss of output, rather than the sorts of things that happened in previous recessions?
Let me tell you, I was at the Bank of Japan in March 2009 when they got the first statement that the year-on-year fall in exports was 70% for Japan. They were horrified. They were listening to my lectures in forecasting, and I told them how to forecast in the face of breaks. And they asked me, what was the forecast for the next months, year in year? And I said 70%, which caused complete consternation. In fact, it was 75%. These methods work. I've got graphs on here that I can show you. We can track the enormous drop in Japanese exports almost exactly using a robust forecasting device once the first ones happened. Right? We can't forecast, I have no idea it's going to fall 75% or 70, neither did they. But once it's happened, you see the data generation process contains the break. It must do. So that then feeds into the growth rate. Okay, that growth rate is a fall of 75%, must carry forward into the next period. If there isn't another break, right, then that will give you an immensely accurate prediction of what's going to happen. Everything you ever wanted to know about forecasting is there. All the breaks, all the parameter shifts, all the emitted variables, absolutely everything is there, and you didn't need to know it. Forecasting doesn't require a decomposition of the model. It only requires a statement of what the next observation will be. And it's a mistake to think you need to learn about the world to make a forecast. In fact, almost all methods of doing that will fail quite dramatically in the face of shifts. But methods that are robust to the shift, because they use the fact that the DGP must have that in it, right? It's happened. Then they will give you good forecasts. And in fact, after the event, we were quite right.
Gilles, last question.
Yet it seems to me that alternatively you could have not a break in the parameters, but just turns out that your disturbance distribution has a fat tail and you get an anomaly. And as a counter example, there is the Portuguese Revolution in 1975, where immediately after the share of wages in GDP shoot to 95%, there was a huge wage push, and then it fell back to normal immediately after. So it's not clear that that was a structural break, or maybe a very temporary structural break.
Yeah, absolutely, Hugh. And one of the biggest issues, and I'm sure the bank MPC spends a long time discussing it, is what we have seen as an aberrant thing due to a break, an outlier, a measurement error, and we have a lot of theory of how you might discriminate between them, not in one observation, that's impossible, but after 2 or 3, you can actually start to see whether it's a measurement error, a permanent shift, or an outlier. Or even a change in the variance of the error, and it's no longer outliers. These are going to happen regularly.
It's the measurement errors that continue. Okay, we'll stop now and thank David and Deborah.